Summary. So turbulence is composed of strong vortices. So we know now that within these vortices, the trend is that particles which are denser than the fluid are going outward, and bubbles which are lighter than the fluid are going inward. And for now, I didn't consider the gravity. Okay, I'm going to talk about the effect of gravity just in a few minutes. Okay, and all this interaction will be stronger or less strong depending on the Stokes number. Okay, so you remember if we define the Stokes number and we compare the time scale of the response of the particle to the fluid element, we will have different. So let's say that we have a vortex like this. We have a vortex like this. We know that a particle is going to spiral out. Okay, so we know that the trajectory will be like that. But depending on the Stokes number, we will have either a gentle spiral like this, or it could be very quick, or it could be very long. Okay, that will depend on the Stokes number, because when the Stokes number is low, the particles are going to follow the fluid streamlines, and when the Stokes number is, let's say, of order 1, then they are going to be expelled very fast. Okay, so the rate of centrifugation will depend on that Stokes number. So this is what is plotted in that pictures. Okay, so here these are experiments that you cannot see very well, and these two are simulations. Okay, so these are simulation and experiments of turbulent flows, and we look at the particle positions at one time step. Okay, so in that plot you may see that you have clusters. You see that you have clusters of bright particles because they have been illuminated by a laser just to see them very clearly, and these clusters means that the particles are not evenly distributed. They have been accumulated in some region of the flow, because in a turbulent flow you have vortices at some places, and they are going to expel the particles outside, and then they are going to accumulate around the vortex. Okay, so this is an experimental visualization of this accumulation, preferential accumulation of particles outside vortices. Okay, so it has been done in the 90s, and it is a turbulent kind of turbulent pipe flow, but with a square channel, with a square section. Okay, these two are simulations because we know now how to simulate the Navier-Stokes equation, so we can generate with CFD a turbulent flow, and here you see the same configuration but with simulation. And the way to analyze this plot is the red region are the vortices. Okay, so this is the region where you have intense rotation of the fluid, and you see that the particles are not evenly distributed. You see that you have kind of clusters, elongated clusters, because these particles are going outside the vortices, and they are elongated. These accumulation regions are elongated by the vortices. Okay, so you see here strong accumulation, strong accumulation, strong accumulation here, strong accumulation, and they are always outside the red region. Okay, so it's not very, sometimes it's not very obvious, because you have to remind that this plot is evolving in time. Okay, it's only a snapshot, but if I take this plot a few seconds later, the vortices are moving. The vortices are moving, and the particles, it took time to go from one location to another location. So maybe a vortex is going to pass over that particles, but they don't have time to go outside. Okay, because this vortex is going to pass very quickly, and then another one is coming. So you have to keep in mind that this picture of particles spiraling outward is just a sketch, because in a real flow, the flow is very complex. But the general trend is to see that the particles are not evenly distributed. Okay, so what you may think initially was maybe in a turbulent flow you place particles and they are going to be dispersed by turbulence, and then the concentration is homogeneous. But actually it's not the case. You see that the concentration, the black region, are very, very heterogeneous. Okay, so you have region of accumulation, and these regions of accumulation are moving in time. Okay, okay, so you have to keep in mind that when the Stokes number is of order 1, this is when you have this type of preferential accumulation. When Stokes number is very low or very high, then very low, the particles are moving everywhere, so they are dispersed. And then the concentration, if I do the same plot with a Stokes number low, much lower than 1, then you see many particles everywhere. You don't see any organization. If you do the same plot, but with a large Stokes number, the particles don't care about the flow, and they just sit, and they don't care. And then the particle concentration is also evenly distributed. Okay, but in between, when the Stokes number is of order 1, 1, 2, 3, okay, then you see this preferential accumulation when the Stokes number is of order 1. And it's very important because it may have some effect. So you were asking me about the effect on possible mass transfer chemical reaction. This is what the people try to prevent, actually, because here, let's say that the particles are catalytic particles which are going to generate heat or some product, then you see that the rate of production will be completely different from that region where you have no particle to that region where you have many, many, many particles. Okay, so all these phenomena are very important for chemical engineering because what you prefer in chemical engineering is to have something which is very, very homogeneous, because you want that the rate of production or the rate of heat release to be constant. But in that case, you see that turbulence, it is counterintuitive, because turbulence is going to generate heterogeneity instead of mixing the system and making that evenly distributed. Okay. So this is another plot, similar comments, but for a different flow. Here it's a turbulent flow in a channel. Here it's homogeneous isotropic turbulence. Here it is a turbulent jet like this. Okay. And again, you see that depending on the Stokes number, so 0.01, 0.1, 1, and 10, you see that when the Stokes number is very low, you see the particles are evenly distributed here over the width of the jet. When the Stokes number is around 1, so you see these braids, these zones of accumulation. So you see here you have accumulation, here you have accumulation, here you have accumulation, compared to there where you have particles everywhere. And when the Stokes number is very high, you see that the particles are moving almost in straight lines. There's very few dispersion. Okay, so this is a different case, but the analysis with the Stokes number is the same. The only point which is difficult with this analysis is the choice of the time scale for the flow. Okay, so you have to think about that. There is only one time scale for the particle, which is related to its size and density and the fluid density. But for the time scale of the flow, you may have many choices, because in a turbulent flow, you have big vortices, small vortices. So you have to think about the good definition of the Stokes number if you want to evidence some physical mechanism. Okay? So now I'm going to talk about the effect of gravity. Okay, so we are going to explain that, but before looking at the answer, we can, yes?
Yeah, we talked about no flow and then turbulent flow. What happens in between in laminar flow?
In laminar flows, it depends on the kind. It depends on the type of flow. So if it's, it will really depend on the type of flow. There's no general answer, because it will depend on the flow structure. So the question was, what can we have some ideas about laminar flows? It really depends on the flow. So let's say if you have a Poiseuille flow, if you have a Couette flow, if you have a single vortex like this, the response will be different. There's no general trend for that case. Do you have something specific in mind? No. Okay. It really depends. It really depends on the flow. Usually it's easier to do, because if the flow is simple, then you can write down a model, an equation. It's easy. For turbulent flow, the people have struggling a lot with that, because the flow is very complex. It's moving in the three directions. It's unsteady. So initially, people you don't know what would be your expectation. For a simple flow, it's easier. It's easier to evaluate the forces and see what is going on. But it will depend on the shape of the flow, on the flow structure. Okay, so now we are going to consider gravity. So again, let's say that we have one vortex like this, and now we have gravity. Okay, so we know that So we know that when we have no flow, we know that if rho p is larger than rho f, the particle is going to settle. And if rho p is lower than rho f, then the bubble, for example, is going to rise. Okay, so the question now is what will happen when this trajectory is going to interact with one vortex, okay, under gravity. So let's say I take one particle like this. So what is your feeling? What is your expectation? What is going to happen to this particle? So rho p is larger than rho f. So we expect that the particle is moving outward the vortex. Okay? So it will remain outward the vortex. Do you know on which side of the vortex it will settle? On the right or the left? Yeah, on the right, of course, because when the particle is approaching the vortex, the fluid is moving in that direction, and because of the drag, particle will be pushed toward that direction. So the particle trajectory will be something like this. Okay? So this is what we expect. And of course, the shape of the trajectory will depend on the Stokes number. If the Stokes number is very low, then the particle is going to follow very closely the vortex and then settle. If the Stokes number is very high, it will almost pass through the vortex without too much deviation. Okay? So this distance is depending on the Stokes number. Okay? So now if I do the same analysis but same prediction for a bubble, so let's say that the bubble is here, so it is rising. So we expect that it is moving slightly on the left because the vortex is rotating like this. But we know that the bubble has the tendency to move inward. Okay, so we expect that the bubble is going to do maybe something like this, and maybe it will go out. Okay, so the trajectory will be completely different because the dense particle is moving outward, let's say along the boundary of the vortex, compared to the bubble which is moving inward, maybe spiraling a bit and then escape from the vortex. So based on that, can you predict if the mean settling velocity of the particle, so the time it takes to move, let's say 1 meter for blue and red, compared to the case of no flow? So the question is, depending if you have a particle, a solid particle or bubbles, what do the vortex? Does it accelerate the settling speed, or does it decelerate the settling speed, decrease the settling speed? Okay, for which case? For the blue or the red? Blue. For the blue, exactly. Okay, because when the particle is moving like this, and it is in this region, it will experience the drag of the fluid, the drag of the vortex. Okay, so here the velocity of the particle will be increased by the presence of the vortex. So the total time necessary to travel this distance will be lower. Okay, so we expect that for particles in vortex with rho p larger than rho f, we expect that the settling velocity will increase. Okay? And we expect the opposite for the bubbles, because when the bubbles is rising, it will lose some time spiraling inside the vortex before the escape. So it's valid for bubbles or drops. Rho p lower than rho f. So rising velocity will decrease. okay? Because you will lose time within a vortex. So this is what we can understand for a very simplified flow when you have only one vortex. But actually, this is what happened in turbulence, okay? Because turbulence is composed of many vortices. So this is what has been done in that studies. So here, this is a collection of different simulations and also experiments, okay? Where you plot the difference between, so this is for settling particles, for dense particles. So you plot the difference between the mean settling velocity, so the time you need to travel a certain distance in a turbulent flow, minus the settling velocity with no flow, the terminal settling velocity. So if it is positive, it means that there is an increase of the mean settling velocity in a turbulent flow. If it is negative, there is a decrease of the mean settling velocity. And what you observe is an increase, okay? And it is just dimensionless by the characteristic turbulent flow, okay? And you observe that in simulations and in experiments, so Yang and Shire experiments, you see that there is a, let's say, between 10 and 20% increase of the settling speed due to the presence of turbulence. And this is the result of the interplay of centrifugal effect. So you see here a turbulent flow. You see that the particles here, you have a strong vortex. You see that you have no particle inside because they are just collecting around the vortices. Okay, so you see all the black regions are the strong vortices. So this is the region of high vorticity. So you see that the particles are in between around the vortices. So you see the clusters formation. And these clusters of particles are settling under gravity. And this is what you expect. So let's say in a turbulent flow, you have different vortices of different sizes, different intensities. But the particles' trajectories is always outside. And with a strong preferential to go on the downward region of the vortex, okay? Because when it settles, it is dragged by the vortex and it will settle on the downwheeling part of the vortex. And because it is on the downwheeling part of the vortex is going to give speed due to the drag to that particle, and then it will facilitate its settling behavior, okay? So this is something which is very, a phenomenon which is very robust. You can see that in experiments, in simulations, and also some theory has predicted this. And it is, of course, very strong when the Stokes number is of order 1. Okay, so you remember, Stokes number lower than 1, it's like fluid elements, so they are going to be dispersed everywhere. Stokes number much larger than 1, it means that the particles is so dense and so inertial that it will pass through the vortex without seeing the velocity perturbation, so there's no effect. So this kind of enhancement of settling velocity can be observed when the Stokes number is of order 1, let's say from 0.1 to 5, okay, order 1. And then you see that you may have an increase of 10% to 20% of the settling velocity. The same experiments, same simulations, same theory has been done for bubbles. And in that case, what you observe is a decrease of the rising of bubbles. Okay, so I don't think I have the, no, I don't have the plot, but I have a similar slide with bubbles about exactly the same behavior, but the rising speed of bubbles will be decreased by the presence of turbulence because bubbles are going to spiral inside the vortex and then they lose time compared to a no-flow case. Okay, so this is what you have to keep in mind. So keep in mind that turbulence is going to mix things, but the particles with Stokes number of order 1, they are not going to be mixed. They are going to be demixed. Okay, you will have strong accumulation. And because of that strong accumulation, if you account for the effect of gravity, then you can generate modification of the mean settling velocity. Okay, so now I'm going to move on the second part, which is what is the effect of particles on the flow. Because now we said, okay, if the system is dilute, you may have accumulation. And if you have accumulation, in that region, maybe you have also modification of the flow, because the particles are going to generate perturbation. So I'm going to talk about two-way coupling. So what we need to do is, so we know how to solve the force balance. We know to predict some trajectories in simple flows, in turbulent flows also. But we need to inject now feedback effect on the fluid motion, on the fluid equation, on the Navier-Stokes equation, because these particles are going to modify the response of the dynamics of the fluid. Okay, so we want to evaluate what is the flow modulation by the presence of the particles through this collective effect, because particles are accumulating in some region of the flow. Okay, so we are going from one-way to two-way coupling. So there is a little part of math, so I'm going to be quickly on that. I will give you the slides for the people who are interested in the equations. But the idea is now to try to write, so these are the Navier-Stokes equations that you have seen with Professor Chakraborty. The question is, what are the modifications I need to do in that equations to account for the presence of the particles? Because of course, if the flow is changing, it means that the equations are changing. Okay. So the way to do that is to do the same momentum and mass balance derivation for the equations, but including the effect of the particles. Okay, and it could be done by averaging techniques, where you have many particles in the domain, and you are going to make a mass and momentum balance on the fluid, which is containing some particles. Okay, so we have now a function key C is actually an indicator. If you are in a point where you are inside a particle, it is 1. If you are in the fluid, it is 0. Okay, so it's a way to discriminate if you are at a position with particles or at a position without particles. And then you make an average of what is going on into the mass balance and momentum balance equation. Okay, so this is what is done here. So I'm not going to comment too much on that. I'm just going to comment what you get at the end, the equations, and see what is the difference between the Navier-Stokes, classic Navier-Stokes equation for single phase, to the two-way coupling equations for Navier-Stokes plus particles or plus bubbles. Okay, so you see that the equations are mass balance for incompressible fluids is divergence of u equal to 0, and this is the momentum balance with u, the pressure, viscosity, and gravity. Okay, so if you look after some calculations, if you look at the equation, you see that they are very similar to the previous one. So you have the divergence of something, but now we are accounting for epsilon, and epsilon is the fraction of the volume which is occupied by the fluid. Okay, so you have, let's say, a system, a two-phase system. So you have a two-phase system with particles, okay? And this is the volume V. So you have, let's say, n particles. So epsilon C is an epsilon P. Epsilon P is the number of particles multiplied by the volume of the particles. So we assume that they are constant over V. And epsilon C is, of course, 1 minus epsilon P, because epsilon C plus epsilon P is 1, of course. Okay, so you have a volume V. Inside that, you have a volume occupied by the particles. So the sum of the two volumes is, of course, V. Okay. So epsilon P will be, if it is 0, it's single phase. So it means if epsilon C is 1, this is single phase. If it's below 1, you have particles in the volume. Okay. So you see that now in the equations, in all the two equations for the single phase flow, now we account for the presence of the particles. Okay, epsilon C is in there, is in there. In all the terms, it is going to be involved. Okay, and of course, epsilon C is not constant, because if you look at that plot, epsilon C here will be low, but here you have pure fluid, it will be almost 1. Okay, so you know, so now epsilon C, this epsilon epsilon c is a function of the position and time. Okay, because in a turbulent flow, the particles are moving, so the distribution of particles, the concentration of particles is depending on the position, but also in time. Okay, so in all these equations, you see that epsilon c is now a function of position and times. And then it will modify all the derivative, okay, because here you have derivative in space, so you have dx over d epsilon c over dx, d epsilon c over dy, d epsilon c over dz, which is depending on the flow structure. And you have also time derivative and so on. Okay, so everywhere in the equations you are going to account for the concentration, the local and instantaneous concentration of particles, and that will modify the Navier-Stokes equation, and of course that will modify the solution of the flow, and then that will modify the dynamics of the flow. And the last term, which is here, is the momentum exchange. Okay, when you write the force balance on the particle, okay, when you write that, when you write this equation, so this is the second Newton law, so you say that the acceleration of the particle is related to all the forces acting on the particles, and many of that forces are related to the fluid action on the particle. And you know the third law of Newton, which is the action-reaction. If the fluid is acting on the particle, of course the particle is acting on the fluid. Okay, so it's like if I pushing you like this. If I push you, actually you are pushing me too also. Okay, so this is the feedback effect of the reaction force between two objects. Okay, so in the fluid it's the same. So for example, the drag is the effect of the fluid on the particle. So you have the feedback effect, which is the effect of the particle on the fluid. Okay, and this is what you see here. Okay, so you have the effect of epsilon due to the presence of particle, but you have also this transfer of momentum because the fluid is giving momentum to the particle, but the particle in response gives some momentum also to the fluid, and this is what is in that equation. And you know that because when you do the force balance, you know exactly what is the force acting on that particle due to the fluid, so you can take the opposite and inject that into the Navier-Stokes equations. And then that will modify, again, the equations, and then that will modify the response of the flow and its dynamics. Okay? So this is the way you can handle the effect of particles on the fluid through the equations. Okay? And if you now simulate that equations in a certain configuration, in a Poiseuille flow, in a channel flow, in turbulence, then you will see that the flow dynamics will be different with and without particles, because all these terms are modified. You have momentum exchange between the two phases, and then the flow structure, the flow behavior will be completely different with particles and without particles, depending if epsilon is close to 1 or not close to 1. Okay, you see, this is the way you build two-way coupling models. Okay. So now I'm going to talk briefly about moving to four-way coupling simulation, because as you increase the concentration, the distance between the particle is going to decrease. Okay, so there are more probability for interaction and collision. Okay, so what is going on when two particles are colliding in a fluid? Okay, so again, you have different configurations depending on the density ratio. So bubbly liquids, suspension, solid liquid suspension, or emulsion with liquid with oil and water, or granular flows, I mean particles in gas, in air. Okay. So maybe we can skip that. And we are going to look at what is going on during a collision between two particles or between a particle and a wall with a fluid. So what you should know is the classic case of the classic case of dry collision. So what I mean by dry is collision in a gas. Okay, so yeah, I cannot. So let's say that this is a particle. So we are in a gas, and then I'm going to, let's say it's a spherical particle. I don't have any spherical particle, but let's say it's a spherical particle, and then you drop it. Oh. So you going to take that one. Okay, this one is more spherical. So you drop it and then you have a collision with the wall. Okay, so depending on the material, if you take iron, rubber, sand, you will have a rebound. Okay, and this rebound is characterized by an elastic coefficient. Okay, so if the coefficient of rebound is 1, this is what we call elastic. So there is no dissipation of energy. So if you go from that distance, it will move back to the same distance, no dissipation of energy. If the material is a bit soft, then you have dissipation inside that solid and inside the particle also, and then the rebound coefficient is lower than 1. Okay, so it will depend on the material. So now the question is, if I do the same experiment, but I trying to account for the fluid flow. Here, this is gas, but I can do the same experiment in a liquid, for example, in water. If I drop a particle in water, how the coefficient of restitution will be modified. Okay, of course, the coefficient of restitution of the material is not modified. Okay, this is wood, this is a particle of rubber, for example. So the rebound coefficient of these two materials is not modified. But during the motion of the particle, you have fluid around. Okay, so and this fluid has to flow because the particle is moving. So of course the fluid has to move. Okay, and this is going to modify the response of the collision. Okay, so this is the experience which has been done here. So you see on that panel a plot of the flow around a particle which is going to collide with a wall. On the left panel, this is numerical simulation with CFD, and on the right, this is the experiment where you do visualization with a laser sheet and you look at the flow structure. So there's a good match. The people were very, very happy to do this comparison. And what you see is when the particle is moving down, so you remember the wake of the particle. We have seen depending on the Reynolds number. So you have this wake, and when the particle is approaching to the contact, you see that the wake is coming here, and then it moves toward the wall and then along the wall. And you have to also to remember that you have fluid here. Okay, so when the particle is coming close to the wall, this fluid has to escape. Okay, so you have to drain that liquid, and draining the liquid needs energy, and the energy which is available is given by the particle. So actually, during the motion of the particle towards the wall, it will lose some of its kinetic energy because of the drainage of the liquid film. And then the rebound of a particle in a viscous fluid should be different from the rebound of two solids in void, okay? Because in void you don't have any friction. In air you have a little friction, but not much, okay? So in a liquid we expect that the collision will be different because you have some energy dissipation due to the liquid film drainage, okay? So this is a zoom. This is a zoom of that situation where the particle is very close to the wall. When the particle is very close to the wall, so you need to drain the fluid, and this is the flow field that you see. Okay, so you see here, this is the middle of the particle, and you see that the fluid has to escape through this very thin liquid film. Okay, and this is going to dissipate energy. So now on that plot, these are experiments and simulations of the effective coefficient of rebound. Okay, so you see that this is the ratio of velocity after collision divided by velocity before collision. So this is the classic definition of the rebound coefficient, restitution coefficient. But now this has been divided by the restitution coefficient of the material. Okay, because if you do experiments with rubber or particle, you have a contact, a solid contact, and then you have a certain value for the restitution coefficient. What you want to see is what is the effect on that restitution. Okay, so this is why we normalize the restitution coefficient by the dry restitution coefficient of the two materials. Okay, and what you see is that depending on the values of, I'm going to explain what, depending on the values of the impact parameters, you go from 0 to almost 1. When it's 1, it means that you have the same rebound than in void, in gas. Okay, so there's no effect of the fluid on the rebound. And when it's below 1, and for example, when it is 0, it means that now you know that there is a restitution coefficient, let's say about 0.9 for the two materials. But because you have the fluid, so actually the particle is moving like this, but it is losing energy because of the fluid drainage, and then it sticks on the wall. There's no more energy available for the rebound. Okay, so it means that although the restitution coefficient of the two materials is 0.9, the effective rebound coefficient in a viscous fluid will be 0, no rebound. Okay? And you go smoothly from 0 to 1 when you vary the impact parameter. And again, the impact parameter is related to inertia because it depends on the inertia of the particle. If the particle is very inertial, you remember, there will be almost no interaction with the fluid. Whatever the fluid, it will pass through the fluid without any interaction, okay? Like in particles in the gas. If the if the particle inertia is quite low, then it will react to that drainage of the fluid, and then the velocity will decrease and maybe 0 at contact. Okay? So the Stokes number is the same as the one that we defined. So it's again a ratio of 2 timescales. So the Stokes number for collisions. So it's actually called impact Stokes number, and the definition is very simple. So it's tau p over tau f, and tau p is 2 over 9 rho p multiplied by r square over mu, and then we are going to make it dimensionless by, so let's say you have a particle which is moving at velocity v and its radius is r. So the time scale of the fluid motion is r over v. Okay? Because this is the time you need to move one radius at a certain velocity v, which is the settling velocity. Okay, so tau f will be r over v. Okay, so you see, you get what is on the board. So r square and v is moving up. So this is the definition of the impact Stokes number. So depending on the ratio of particle response time to this time scale, you may have no rebound. So the effective coefficient of restitution is 0. So the particle will collide and stick on the wall. And you go smoothly to almost 1, which is what we call the dry rebound. And this is what you get in gas, for example, or in void, but most likely in gas. Okay? And you see that it is, it could be very, in terms of suspension dynamics, it could be very different. If you make an experiment within a liquid or within a gas, the particles are going to collide, but if the Stokes number is different, you may have particles colliding like this, and some of the particles are going to stick together because the collision is almost with 0 rebound coefficient. Okay, so you see that when you move to these dynamics, the four-way coupling effect, you need to account again for the effect of the fluid through the drainage of the fluid. Okay. Okay, so here this is what you see when you vary the Stokes number, and the plot here is the agitation of the particle, the kinetic energy. So let's say you have a shear flow, then because you have a shear flow, the particles are going to collide together, and depending on the Stokes number, we plot the evolution of the agitation of the particle. Okay, so the rate of fluctuation of the particles, and depending on the Stokes number, so depending on that Stokes number, you see that the agitation of the particle may vary by 4 decades. So you see, it's a very, very, very dramatic effect. Okay, so if you have low Stokes number, the particles, because of the shear, are going to collide. They are going to stick together, so you don't have much fluctuation. But when the Stokes number is high, you are in that regime where you have almost elastic collision, and then you have like balls for the BR. You know the BR, the game with the cube. So you have the particles are moving like balls like this, and then it is fluctuating a lot. Okay, so this is what you see on that plot. Okay, so you have when the Stokes number is moving from 1 to let's say 10 or 100, you see that you span almost 4 decades of agitation. Okay, so usually when you are in that regime, this is liquid-solid suspension or emulsion, so there's low agitation due to the collision. And when you are in that regime, this is usually gas-particle suspension, where the particles are moving like balls. Okay. So now I'm going to conclude on that section, showing you few effects of the particles on turbulence, because there's a feedback effect on the turbulence when you have collision and all these effects. And this is still open. So this is, I'm not going to comment too much because that would be very complex, because we don't have the good answer. So I cannot tell you the answer. So I can talk about what the people are doing in research, but then it's not really a lecture because I'm not going to give you any answer at the end. Okay, so the question is very simple. You take a turbulent flow, and then you seed that flow with particles. And the question is, the flow, will it be more or less turbulent? So it seems to be very simple as a question. It's very fundamental. So if I seed the turbulent flow with particles, will you observe an increase of the fluctuations or a decrease of the fluctuation? Okay, the particles are going to damp or to enhance the turbulence. And the question is completely open, so we don't know. So we don't know because it is depending on many parameters. It will depend on the size of the particles. It will depend on the density of the particles. It will depend on the relative size of the eddies of the turbulent flow and the particles. And it will also depend on the configuration, if you include the effect of gravity or not. Okay, so you have many parameters, and you see on that map, which has been proposed by these guys, that they observe sometimes a reduction of turbulence and sometimes an amplification of turbulence. Okay, so the question is not universal. You cannot tell to anybody, yes, if you place particles, you will reduce turbulence or you will enhance turbulence. Sometimes it will reduce, sometimes it will enhance. Okay, and this is another, so here, this is some simulations. Here, this is some experiments. Again, very simple experiments, very fundamental, simple experiments. You take a pipe flow, okay, so you flow water through that pipe flow, and you may know that the Reynolds number for the onset of turbulence is about 2000, okay, between 2000 and 2500. And the question is, if I seed that pipe flow with particles, the transition to turbulence, will it be lower or higher than 2500? Okay, and again, the answer is, so these are experiments, so they did experiments in a pipe flow and they measured the onset of turbulence with different concentration, volumetric concentration of particle on that axis, and with different size ratio. So D is a pipe ratio, D is a pipe diameter, and capital D, and D is a particle ratio, a particle diameter. So you see, D over D is very small particles, D over D20 is big particles, okay? And depending on the size of the particle, depending on the concentration, sometimes you have a delay of the onset of turbulence, so above 2000, and sometimes you have an enhancement of turbulence, so the Reynolds number, the critical Reynolds number, is below 2000, so you see you can decrease by a factor of 2, so from 2000 to 1000 if you seed the pipe with particles. But the response is non-universal because it could be below or above the single phase turbulent Reynolds number. Yes.
Yeah, in simple terms, can we not visualize this way that if I have a very small particle, so that means it is getting within the basically turbulent eddies, so it will try to dampen the intensity of that.
Mm-hmm.
Okay. And if I have a bigger particle, so it is just passing through that.
In So just I answer your question. The question is what can we see that? And you are talking about settling. Okay, so I didn't mention that these experiments have been done with neutrally buoyant particles.
Oh, okay.
There's no settling.
Okay. Okay. No, actually, the bigger particles will always say create more say, turbulent eddies because of the displacement of fluids.
Not really. When you have settling, it's what you say is true. So when you have a big particle which is settling under gravity, then you have all these vortex shading, and then this is what we expect. We expect that the particles, because of gravity, are going to give energy to the system and enhance turbulence. When you have a big particle neutrally buoyant, it will almost follow the fluid. There's no wake actually. So this is why it is. These results are very unexpected. We are still working on. This is part of my research activity. So we are still trying to understand what is going on in this system, because the small particle effect is quite well understood actually with what we said. With effective medium we can understand, but the effect of big particle is very tricky.
For dampening also, is there any well validated model?
No.
There is only the band raised one you use.
No? For now, really the question of the modification of turbulent flow by bubbles, by particles, by drops is completely open. We have some models, but we don't know exactly what they are. They are doing something if you do the simulation, but is it relevant compared to experiments? It's completely open. Yes?
What is this Reynolds number? This is the transition Reynolds.
Yes. So you see, for a pipe flow, 2000 is a classic transition Reynolds number. If you don't take any care, if you just do an experiment in a pipe in your lab with a pump, this is classically between 2000 and 2500. If you take care, you may change that a bit. But if you do classic experiments, this is 2000. And then here they place particles, so neutrally buoyant particles, and they look at the way the suspension is going to turbulence. And you see that you may decrease by a factor 2, which is it is significant. It's not 5%, 10%. It's a factor 2. You can modify the threshold of the instability, or you can delay the instability with many small particles. Okay, so this is still under research. So these are different configuration and different teams that are working on that question, which is very simple. You see, the question is very simple. The answer is very complex. We don't know yet. And last slide, just to explain you why it is very complex. It's because the onset of turbulence is very progressive. Actually, it's not like if the flow is becoming turbulent everywhere like that. Actually, it is becoming from very subtle instabilities close to the wall. And for now, we don't know how the particles are going to modify these instabilities, which are leading to the onset of turbulence. So we do experiments, we do simulations with pipe flows, with channel flows, with shear flows, trying to understand what is the interplay between the particles and the turbulent flow. Okay, trying to get the answer about that. And this is the type of simulation that we do. So you see it's very precise simulation where we simulate the motion of each particle and also the flow around each particle to see what is the modification of the flow dynamics when we are very close to the transition to turbulence, to see if the particles are going to trigger the onset of turbulence. So it is completely open, but I just wanted to mention you that the question is completely open, and for now you cannot tell if the particles are going to dump or to enhance the turbulence level in a general case. Okay, we may know that for very small particles, we may know that when the settling is very intense, but in the general case we cannot predict. Okay, you have a particle. So the question was what is the effect of particle on the flow when you don't have any settling? Okay, when you have settling, it's obvious because we know that you have eddies, you have there is a specific thing when this particle is placed in a straining region, so in a region of the flow. So you know that the flow is composed of vortices and region of high deformation. When this particle is in this type of flow, if it was a drop that could deform, it will move like this. Okay, it will elongate because the flow is going to exert tension on the drop. But because it is a particle, it cannot deform. It is solid, so it will resist to that forcing of the flow, and then it will generate some stress inside the liquid, and this stress is going to interact with the flow instabilities. So this is what we expect.
If there is a gentle flow and then there is an obstruction, so you can find some turbulences also.
Yeah.
Many times. And many times you find that if there is a turbulent flow, that is totally getting succumbed to.
Exactly.
So this is what you are
This is what we expect. So, but for now, we are not sure on what is the effect of the size. Because you may have different sizes, but this is the mechanism we expect.